The applications of the mean value theorem and Riemann sums in the real world. The goal of the experiment conducted was to demonstrate the mean value theorem in estimating integrals using Riemann sums in the real world. In my experiment, I drove a car a certain distance and recorded the time it took to travel that distance. Then, I used my cell phone to record the timer, speedometer, and odometer. The mean value theorem. The mean value theorem states that if a function on the interval a to b is continuous on the closed interval and differentiable on the open interval, there exists a value c on the interval a to b such that f prime of f of b equals f of b minus f of a over b minus a. Essentially, this equation demonstrates that in a differentiable and continuous function, there is a value c at which the average slope is equal to the slope of the tangent line at point c, f of c, which can be seen in the graph below. How I applied the mean value theorem. Throughout the drive, the velocity was always positive, as the car was always moving forward. This proves that the distance-time function is both continuous and differentiable, which is the first step in determining whether or not the mean value theorem can be applied. In the experiment, the car traveled a total distance of 1 mile, or 5,280 feet, over a duration of 161 seconds. This leads to an average velocity of 32.795 feet per second. Mean value theorem states that this instantaneous speed must be reached at least one time during my trip. The car reaches this average velocity of 22.36 miles per hour at these times listed below, on the interval from 0 to 161 seconds. Riemann sums. Riemann sums are approximations of integrals that use small rectangles that enclose minute amounts of the curve and sum them all together to get a close estimate of the area under that curve. They are useful when an equation for a function is not provided, but intervals of x and y values are given. In my experiment, I used the recording of the speedometer and timer to determine the velocities of the car at 7 different subintervals, every 23 seconds, as seen in the table below. Riemann sums require me to sum the areas of the rectangles. The area of a rectangle is base times height. The base here is represented by the interval of 23 seconds. The heights are the 7 leftmost points or velocities. As shown, the results are 4,992.5 feet, which shows this is an underestimation of the 5,280 feet, or 1 mile, that I drove. As for right Riemann sums, everything is the same. The base is still 23 seconds, but the heights are now the 7 rightmost points or velocities. Calculating this, I got 5,768.399 feet. This number is an overestimation from the 5,280 feet I drove, which leads to the following conclusion. As we can see in the graph depicted, a left Riemann sum of an increasing function is an underestimate, and a right Riemann sum of an increasing function is an overestimate. In the previous two slides, we determined that our left Riemann sum was an underestimate and our right Riemann sum was an overestimate. Using this data and the graph shown, it can be concluded that the velocity function is increasing for a longer period of time than it is decreasing. This means that the car is accelerating for a longer duration of the drive than it is decelerating. The results from the experiment conducted and the data found can lead to the conclusion that calculus can be found in our everyday lives. Different theorems and topics of calculus can be applied to almost everything we do, from driving a car to catching speeders. As demonstrated in the experiments, the mean value theorem was shown to be valid, and the Riemann sums were useful in helping me apply real-world calculus problems.